Hello everyone, welcome to Aero Mechanology channel. Today's topic is fatigue analysis. Fatigue analysis is a critical process in mechanical engineering that evaluates how a material or structure will withstand cyclic loading over time, specifically predicting when failure might occur due to repeated stress or strain. Unlike static failure, which is caused by a single load event, fatigue failure happens gradually and can lead to catastrophic failure after many cycles of load, even if the loads are below the material's ultimate tensile strength. Definition of fatigue analysis. Fatigue analysis aims to predict how long a material or component can endure fluctuating or cyclic loads, the number of cycles a material can handle before cracks start to form, and the conditions under which these cracks propagate and eventually cause failure. Fatigue occurs in three primary stages. Crack initiation, where microcracks form at stress concentrations like notches, holes, or sharp edges. Crack propagation, where these small cracks grow with each load cycle. And finally, final failure, where the crack reaches a critical size, leading to sudden fracture. Key concepts in fatigue analysis. Stress cycles are load fluctuations that occur over time, usually characterized by their amplitude, frequency, and mean stress. The SN curve or Wöhler curve is a graph showing the relationship between stress, S, and the number of cycles to failure, N. Lower stress levels allow for more cycles before failure. The endurance limit is the stress level below which a material theoretically will not fail, regardless of the number of cycles, which is applicable for ferrous metals like steel. Lastly, the fatigue limit is the highest stress level a material can withstand for an infinite number of cycles without failure. Types of fatigue loading. High cycle fatigue, or HCF, occurs when the loads are low, but the number of cycles is very high, often reaching millions of cycles. On the other hand, low cycle fatigue, or LCF, happens when loads are high and the material undergoes plastic deformation, leading to failure in fewer cycles. Application of fatigue analysis. Fatigue analysis is crucial in industries where components are subjected to repetitive loading, including automotive, aerospace, civil engineering, and marine. In the automotive industry, parts like suspension systems, crankshafts, and engine components are subjected to repetitive stress during normal operation. In aerospace, aircraft wings, fuselage, and engine components undergo cyclic stresses due to changes in pressure and temperature during flight. Civil engineering structures, such as bridges, cranes, and buildings, experience fluctuating loads from vehicles, wind, or environmental factors. Lastly, in the marine industry, ship hulls and offshore structures, like oil rigs, face cyclic loads from waves and operational conditions. Example of fatigue analysis. Imagine an aircraft wing that experiences varying loads during flight due to turbulence, which causes fluctuating lift forces on the wing. Takeoff and landing also introduce high stress as the aircraft gains or loses altitude. The fatigue analysis of the wing would involve several key factors. First, material selection. aluminum alloys, commonly used for wings, are tested for their fatigue strength. Next, loading conditions. Analyzing how many cycles or flights the wing can safely endure under expected load variations. Stress concentration areas are particularly important. Attention is given to joints, rivet holes, or welds where stress concentrations occur, as these areas are prone to crack initiation. The SN curve for the chosen aluminum alloy helps engineers predict how long the wing will last before cracks begin to form. If analysis shows that cracks could form after 100,000 flights, preventive maintenance schedules are created to inspect and repair potential crack sites before failure. Key steps in fatigue analysis. Fatigue analysis involves several key steps to assess whether a part can safely withstand cyclic loading. First, define loading conditions. Identify the cyclic loads, such as mechanical stress, vibrations, and thermal cycles. Consider the amplitude, frequency, and mean stress. Second, material selection and testing. Select materials based on their fatigue properties and conduct tests to generate SN curves for the material under expected load conditions. Third, identify critical locations. Focus on stress concentration points where fatigue cracks are likely to form, such as sharp edges, holes, and welded joints. Use finite element analysis, or FEA, to predict stress distribution across the component. Fourth, crack initiation and propagation analysis. Estimate the number of cycles to crack initiation using the SN curve or strain life approach. Use fracture mechanics to predict how cracks will grow once they are initiated. Finally, safety factor and life prediction. Apply a safety factor based on the criticality of the part, with aircraft parts requiring a very high safety factor. Estimate the component's life under given load conditions and determine when inspections or replacements are needed. Benefits of fatigue analysis. Fatigue analysis prevents unexpected failures by allowing for the prediction of when a component might fail under cyclic loading. It enhances safety by ensuring parts in critical systems like aircraft, automobiles, and bridges remain operational within safe limits. It also optimizes maintenance schedules, allowing for preventive maintenance to be planned based on the expected fatigue life of the component. Additionally, it reduces costs by preventing costly repairs and downtime through early identification of potential fatigue failures. Fatigue analysis is essential in ensuring the longevity and safety of components subjected to cyclic loading. It helps engineers design parts that can withstand repeated stresses without failure and allows for the optimization of materials and maintenance practices across industries. From automotive and aerospace to civil and marine engineering, fatigue analysis is a cornerstone of safe and efficient design.